Once again, I welcome you all for this video lecture. In the previous video lecture, we discussed some of the properties of CTFS like linearity, time shift, frequency shift, as well as the time scale. In the today's video lecture, we'll be discussing about the few more properties of continuous time Fourier series. And whatever the properties we study in the today's video lecture, they are very important when you study the subjects related to signal processing as well as communication system. And here the property is the convolution. Means whenever we perform the convolution between the two signals like x of t and y of t, what is the resultant convolution in Fourier series domain? Means frequency domain. So now let us look into a statement. If x of t, the Fourier series of x of t is capital X of k, which is a frequency domain of x of t, and the Fourier series of another signal y of t is y of k, which is the frequency domain representation of time domain signal y of t. The convolution between these two signals is defined by signal z of t, which is x of t convolution with y of t. And the star operator denotes the periodic convolution. And when there is a convolution between the two signals, and when you apply the Fourier series over this, the resultant frequency domain representation will be z of k, which is a Fourier series representation of z of t, is equal to the fundamental period t into the Fourier series representation of x of t is x of k multiplication. It is a simple multiplication here. And the Fourier series representation of y of t is given by y of k. So here, in simple meaning, whenever there is a convolution between the two signals in time domain, in Fourier series domain, it is the simple multiplication of the same two signals but in frequency domain. So now let us prove this property, and we know that the Fourier series representation of any time domain signal x of k, that is the Fourier series of x of t is given by x of k, which is 1 over t integration over the fundamental period t x of t multiplied by e raised to minus jk omega naught t into dt, where omega naught is the fundamental frequency and capital T is fundamental period. Similarly, we can have the Fourier series representation for y of t, which is given by this equation. And the convoluted signal is denoted by z of t, and its Fourier series will be given by z of k by this equation. And we know that this z of t is the convoluted signal for x of t as well as y of t. So let me substitute z of t as here inside the integration x of t convolution y of t followed by this exponential signal remains the same, that is e raised to minus jk omega naught t to dt, right? So it is 1 divided by t integration over t. Now we know that whenever there is a convolution between the two time domain signals, their convolution operation is performed by using the integral convolution, right? And that is expressed as integration. Since we have already t here, just to avoid the confusion, we'll take another parameter L here. So L is equal to fundamental period t. Now it is x of L into y of t minus L. The conventional definition or formula is what? X of tau into y of t minus tau. So here I have taken the parameter L. So this becomes x of L into y of t minus L into dl followed by this exponential signal. Now let us change the order of integration here, right? So we have two integration. One is with respect to capital T, is another with respect to L is equal to capital T, right? So we'll interchange these, right? in order to make the simplification much easier. So 1 by t I will keep as it is. This inside, sorry, this inside integration will take outside, and the outside the integration goes inside here. And I will combine this x of L with the outside integration, and the remaining y of t minus L is with the inside integration multiplied by e raised to minus j k omega naught into t dl into dt. Since in the second integration we have y of t minus L, so we have to make some substitution here. So let me substitute t minus L is equal to M. And since here it is dt, we have to differentiate t with respect to what? dm. So we'll get dt is equal to dm. So now let me make use of these things in the above equation, that is integration equation. So it is 1 by t integration x of L into m. Now it is, yeah, t becomes what? M. So dt becomes dm and t becomes m. So m is equal to capital T. And y of this t minus L becomes m e raised to minus j k omega naught. Now t minus L is equal to m is there. So what is there for t? The t value becomes m plus L. So that I have substituted here, right? And dl is as it is. Now this dt becomes dm, right? So it is 1 by t x of L. Now, since it is x of L associated with this integration, it is a function of a parameter L. So look at the two here exponential. If you simplify, you will get the two exponential signals with different parameters associated with j k omega naught. One is m and another one is L. Since the first integration is associated with parameter L, so let us combine the exponential which is having L term into dl, and the second integration m is equal to t will collect all the terms related to m here, y of m multiplied by e raised to minus j k omega naught m into dm, right? See, it is 1 by t will keep as it is, and we know that x of k is equal to, or you take x of k or you can take y of k, anything, right? So x of k is equal to, you look at the first equation here, x of k is equal to 1 by t integration x of e raised to minus j k omega naught t into d, right? But here in this integration, right, we don't have 1 by t here, right? So if I take this t this side, so we can write this integration x of L into e raised to minus j k omega naught L means this t, it comes this side, then it becomes t into x of k. So that I have written here. So the simple, right? So the simple this integration expression becomes t into x of k. Similarly, this you can written as t into y of k, right? So in this t and this t get cancelled, and one t you can write here, and x of k into y of k, right? So here, except this fundamental period t, it is the simple multiplication of the same two time domain signals but in frequency domain. So x of capital X means it is frequency domain signal, small x means it is time domain signal. This you have to remember, right? And coming to the second property, that is a modulation, which is a very important, right? So what is modulation? The basic meaning of modulation is, so we mainly use this terminology, modulation terminology, and we study the communication system, right? So the basic meaning of this modulation is the multiplication of two frequency signals, right? So x of t is one signal and y of t is another signal. And when you multiply these two signals, that gives the modulated signal. And that process is known as what? Modulation, right? So this x of t is maybe having different frequency and this y of t is having different frequency. You can multiply any two signals with different frequency, right? So again, let me start with the statement. If x of t is equal to x of k with fs Fourier series, and the Fourier series of y of t is y of k, and now let us perform the modulation. Modulation means the simple multiplication of these time domain signals, x of t and y of t, and this product is assigned to a signal z of t. And when you take the Fourier series over this, z of t becomes what? Z of k. And now, when you take the Fourier series, the simple multiplication between the two signals in time domain becomes the convolution between the same two signals but in frequency domain. Here you can observe this is star. So it is a convolutional operator, right? And here we have simple dot, means it is a simple multiplication. And the Fourier series of this simple multiplication results into the convolution between the same two signals but in frequency domain. So that is the meaning of this modulation property. So now how to prove this? Again, let me take z of k, which is a Fourier series representation of a periodic signal z of t given by this expression, right? So we'll be seeing this equation from many properties, and this z of k is equal to 1 by t, and let us substitute what is z of t. It is a simple multiplication of x of t and y of t. So that I have mentioned here, followed by exponential term, right? And from the definition of periodic signal x of t, right? So if you know the Fourier series coefficient x of k for the periodic signal x of t, right? So in terms of Fourier series coefficient x of k, we know that how to represent this x of k, how to express using the summation, right? So in the very first class of the Fourier series, we discussed the two equations. One is analytical equation and another one is the synthetic equation. So this x of t is given by summation L is equal to minus infinity to plus infinity x of L, just to avoid the confusion, right, between k, between t and that. So I have replaced t by what? L here, right? Summation L is equal to minus infinity plus infinity. Here it is capital X of L, means it is the Fourier series coefficient of x of t multiplied by, remember it is not minus, it is e raised to plus j L omega naught into t, right? Now let us substitute this x of t in terms of summation in the equation number 1, right? Before this y of t. So z of k is equal to 1 by t integration. Let us substitute this x of t here. So that is summation x of l e raised to j l omega naught into t, and followed by the remaining terms y of t and e raised to minus j k omega naught into dt. Since we have integration as well as summation, in order to get the required proof, the final answer, we have to make some arrangement here, means changing the position or order of summation and integration with respect to the arguments or parameters, right? So now let us see how to change 1 by t, right? So now let me take this summation outside. So later understand why we take the summation outside, right? Summation I will take outside first along with x of l. Then we'll take integration y of t into e raised to minus j. And here, if you see these two, the omega naught t j is common, and here we have l and here we have minus j. So we can write here e raised to minus j k minus l omega naught t into dt, right? So it is summation x of l. Now again, when integration of y of t into e raised to minus j k minus l omega naught t into dt, right? So I can write integration z of t e raised to minus j k omega naught t into dt as only this term, except this 1 by t, by only this expression I can write as t into z of k. That is one thing. And now, in place of, if I have in place of k, if I have k minus l, then I can write here this k you can replace by what? K minus l. So integration from t z of y of t into e raised to minus j k minus l omega naught t can be written as what? T into z, means here I have y of t, so it becomes capital Y of k minus l, right? And this t inside, whatever the t we have inside the square bracket, this t and outside 1 over t, this t get cancelled. So we'll be having only summation L is equal to minus infinity to plus infinity x of L into y of k minus L, right? So it is just like what, right? It is a discrete time convolution. Whenever the two signals are discrete time signal, to perform the convolution, we have to use the convolution sum, where instead of integration, we have to use the summation, right? Irrespective whether it is frequency domain or the time domain, it is a convolution sum, and according to that, this can be written as x of k into, that is not into, convolution with y of k. Understood? So the LHS part is the simple multiplication of two signals in time domain, and after performing the Fourier series, in RHS what we got is the convolution between the same signals but in frequency domain, that is Fourier series representation. And moving on to the next property that is very important, known as the Parsevels theorem, right? And according to this Parsevels theorem, what it says is, if the Fourier series of x of t, Fourier series of any periodic signal x of t gives x of k, then we can write 1 by t integration x of t square into dt, right? And you just recall the concepts like the energy and power of the continuous time signal as well as discrete time signal. For any continuous time signal x of t, its average power is calculated by what? 1 divided by the fundamental period t integration from minus t by 2 to plus t by 2, or minus infinity to plus infinity x of t square into dt. Means this LHS part gives you the average power content of the periodic signal x of t, and this is equal to, you have to prove summation k is equal to minus infinity to plus infinity x of k square, right? So x of k is the Fourier series representation of x of t, and when you take all the squares of all the values and if you take the weighted sum, that gives the energy part, right? The energy content. So this we have to prove. The average power of a signal x of t in time is equal to the energy of the same signal in frequency domain. So that is the meaning of the Parsevels theorem. So how to prove? The LHS of above equation 1 is the average power of a periodic continuous time signal x of t with fundamental period t, as I said, right? So that is p is equal to 1 by t integration x of t whole square into dt. The same equation can be written as, right, x of t into x star of t, right? So if both are real, then it is not at all problem. If it is complex, right, if you multiply and take the magnitude, again you will get the same signal. So I can write x of t square as x of t into x star of t, where x star of t is the complex conjugate of the signal x of t, right? So what are complex conjugate means? Complex conjugate means if a complex number a is equal to x plus jy, then its complex conjugate is given by x minus jy. Just to change the sign of the imaginary part of the complex value, right? And here 1 by t integration x of t, and this x star of t, right? X star of t is given by what? Again by the definition of periodic signal in terms of the Fourier series coefficient. Summation k is equal to minus infinity to infinity. X star of t is there, so I will take x star of k e raised to minus j k omega naught into d, right? Again, so the similar kind of the expression we considered in the previous property. Changing the order of summation and integration, we get t is equal to 1 by t summation minus infinity to infinity. So let me take summation and it is x star of k outside, and integration x of t e raised to minus j k omega naught into t, right? So again from the definition of Fourier series coefficient x of k, so I can write this one as what? X of k, right? So it is actually t into x of k, and this t and this 1 by t will get cancelled. You will get only x star of k into x of k, and this can be written as mod x of k square, and this is nothing but what? RHS. And LHS is what? This part, p is equal to 1 by t integration x of t square into dt, that is equal to the energy content mod x of k square within the limits minus infinity to plus infinity. So this is about the Parsevels theorem. And one more small property, but it is very important, right? So that is the symmetry property, right? So if you understand all these property thoroughly, then whatever the subject you will have in coming semester, so most of the things are based on these properties, right? So that's why it is necessary to understand thoroughly the symmetry property. If x of t, the Fourier series of x of t is x of t, right? Then if x of t is a real valued signal, then its complex conjugate of the x of t in frequency domain, right? So if x of t complex conjugate of this x of t is given by x star of t, which is equal to x of minus t, right? So we'll understand later. You will understand later. Just remember, x star of k is equal to x of minus t and real. If x of t is real and even, real valued and even signal, then imaginary part of that x of k is equal to 0. And if x of t is real and odd, the real part of that x of k is equal to 0. Right? So what I can suggest you is just remember these three conditions, right? So we'll understand in upcoming lectures what do we mean by these three conditions when we discuss the Fourier transform, right? So with this we conclude the properties of continuous time Fourier series, and in the next video lecture we'll be discussing about some examples, how to solve the examples related to the Fourier series and how to sketch the spectrum as well as the phase. Thank you.